last day of Scifest Africa 2016. Many of you have met the man that I'm going to introduce this afternoon, who is not only the Deputy Chief Technologist of NASA, but is also an advisory committee member of Scifest Africa and a great friend of this festival. Jim, as the Deputy Chief Technologist of NASA, is in charge of all the technology developed by the agency to go to Mars, but also for all the missions that fall under the name of the agency or under the work of the agency. He also oversees all the field centers, the offices of the chief technologists at those different field centers. How many are there, Jim?
10.
10 field centers across the US. And so they report to Jim as well, and in that respect, he then oversees the work being done at those field centers. Before that, he was the Deputy Director of Planetary Science for NASA, also based at NASA headquarters in Washington, D.C. How many missions, Jim?
30.
More than 30. He's lost count. So really, in terms of the work that NASA has done, the technology that's developed by NASA, I don't think there's anybody in the agency who could tell us more about that than Jim. And before he was the Deputy Director of Planetary Science, he worked at Goddard Space Center in Maryland, just outside DC, where he really had various hats to wear, and you can chat to him about that afterwards. He's won several medals at NASA, so you're kind of part of the furniture at headquarters. But Jim, there is great respect for the work that you do, the work that you are leading as well at NASA, and it's an absolute honor to have you at Scifest Africa. Welcome.
Thank you. Thank you. Thank you so much. Very kind words, Anya. So we have a mix of audience today, right? Some of the more mature, can I say that? And some of the up-and-coming scientists from South Africa. We had a chance to talk earlier. How many of you know what Mars is? Please tell me you know what Mars is. Mars is a planet. Awesome. Is Pluto a planet? Oh. That's too bad. We could talk about Pluto another time. Yes, so NASA has been exploring Mars since 1976, when we landed the Viking landers on Mars. And over the decades, we have been sending robotic missions to Mars as precursors, predominantly because we're trying to understand the science of Mars. What happened to Mars? Why is it not like Earth? And maybe Mars holds a clue to the Earth's destiny as we begin to study it. In addition, the United States has also been interested in sending humans to Mars. We sent humans to the moon, and now the next logical place to send humans is actually to Mars. And so we're using the science of Mars to help inform the mission to Mars. Today, what I thought I would talk about is a little bit about how we might get to Mars. Unfortunately, what I don't have for you is a sweet, laid-out architecture that says first you launch that, and then you launch this, then you launch that, and then you can send humans to Mars. It's not quite as simple as, like, Matt Damon in The Martian, but it is actually very real. And I can talk to you about the technologies that we're going to put together in order for humanity to go on to Mars. So with that, what I thought I'd do is start with a quick overture of what's at Mars now. And I mentioned the Viking landers. There's actually 2 of them. You can find the other one. There's been a number of orbiters at Mars, so these are satellites that don't land, right? And they tell us, they give us reconnaissance information, pictures from the up above, so that we can begin to figure out where we might put the landers. Like, here's the Mars Exploration Rover Spirit, which is no longer operating. It actually had an interesting end. It was traveling along, and these rovers were supposed to last 90 days. This one, I think, lasted like 7 years, right? In fact, it had gotten to the point where one of the wheels wasn't working properly, and so we were driving it backwards just to get it around. And one day, we drove it into a region of the surface that we didn't fully understand, and it got caught in a sand pit. And no matter how hard we tried, spinning the wheels this way, spinning the wheels that way, we couldn't get it out. So it sat there, and we used it as a weather station for a little while, but then when winter came, it froze up and it broke, and that was the end of the very long life of the Spirit rover. The Mars Exploration Rover Opportunity was launched and landed in roughly the same time frame. It's almost an identical twin to Spirit, but it's still going. We've been very careful about how to drive it, and it is still operating. Very important to me, and I'm going to talk a little bit more about Curiosity. Curiosity is a very large rover. Not only is it large, instead of being, there it is, instead of being, these are powered by solar arrays. See the solar arrays on them? Instead of being powered by solar arrays, it's nuclear powered. It's got a radioisotope thermoelectric generator. It takes heat and converts it to electricity. So if these were designed to last for 90 days and they lasted close to 10 years, if this one's designed to last 2 years, it might be lasting for 2 decades. We'll just see how far it goes. But we have a lot of assets on Mars. None of them are human beings. I'll just get that really clear right now. There's no human beings on Mars. And in fact, Steve Squires, who was the principal investigator for the instruments on board these 2 rovers, has been quoted as saying, all the science that's been done by those 2 rovers in the extended lifetime that they've had could have been done in 1 week if you'd sent a human geologist to the surface of Mars. On the other hand, sending these 2 rovers and operating them for 10 years has been much more affordable. And so the idea of mounting a human mission to Mars is daunting just from a technological standpoint, but also from a cost standpoint. It's a thing that most engineers would say we could never afford. We're going to try. We're trying to figure out how to put it into the budget. Let's see, what else we got? Oh, so here's what we did for the Curiosity rover. We put it on top of an Atlas V rocket, which is a medium-sized rocket. When we did that, at the time of launch, it weighed 4 tons, right? We launched it, sent it on a trajectory to Mars. It took 8.5 months for those 4 tons to get to Mars. 8.5 months, right? That's pretty standard, right? And then we had to land it. So it's going, and I always forget the number, I should memorize it, but it's like 13,000 miles an hour. It's like going really fast. And it has to come to a complete stop in 7 minutes. And this is how we did it. Deputy Chief Technologist can't operate a computer.
When people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought, but it still looks crazy. From the top of the atmosphere down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive or dead on the surface for at least 7 minutes.
Entry, descent, and landing. We've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow constrained space. This is one of the biggest challenges that we are facing, and one that we had never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it'll only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we've got to cut it off and then come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical divert maneuver. We fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of a crater, right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms and it could damage instruments. So the way we solve that problem is by using the skycram maneuver.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit it on its wheels on the surface.
As the rover touches down and is now on the ground, the descent stage, it's in a collision course with the rover. We must cut the bridle immediately and fly the descent stage to a safe distance from the rover.
So am I still on? So that is how you land a rover on Mars, or one way that you land a rover on Mars. One of the interesting things about that particular concept is some of the engineers, the first guy speaking, Adam Stelzner, is an acquaintance, and one of the things he told me was the way they came up with that concept to lower it on a crane, which is pretty unusual, by the way, was a college intern suggested the idea, who had been working at the Jet Propulsion Lab, and they were struggling with the problem of how do you land the rover without covering it with dust. And he came up with that idea, and then they took it and they ran with it, which is really kind of cool. That's innovation in practice. Remember I said that the rover on the top of the rocket weighed 4 tons. The rover, when it landed, when we were all done with all of that, 8.5 months journey to Mars, then 7 minutes of entry, descent, and landing, weighed 900 kilograms. So that's a gear ratio. We call that a gear ratio of 4 to 1, right? We had to launch 4 times as much stuff in order to land on the surface of Mars 1 ton. That's important because it's estimated that when we want to send human beings to Mars, we need 40 tons of stuff on the surface of Mars. So launching 40 tons of stuff to the surface of Mars and landing it this way becomes almost unfeasible. Infeasible? Somebody in English can correct me. Anyway, so there's been a lot of discussion about architecture. How do you get that much stuff? You know, even if you use the factor of 4 gear ratio, how do you get 160 tons launched in the first place? And there's been all kinds of ideas. Even school kids have been putting things together. This is a really cool kind of chart that NASA uses from time to time. It's called a bat chart because you take off from Earth and now you're hanging upside down from Mars. Once you get off of Earth and you land on Mars, now you're kind of like upside down. So they call it a bat chart. But you can see that it takes a rocket to get there, and then more rockets, and then ultimately you take the big rocket to Mars, which takes the human beings, and then once they're done, they have to take off and come back. That's pretty much the whole concept. By the way, I love the fact that they drew Batman in here swinging from a cable. That's probably the easiest way of getting to Mars. So over the years, NASA has developed their own bat charts. And this is just one of the concepts. But fundamentally, and I'm not going to go over this in detail, but fundamentally what we need to do is we need to launch some stuff, probably assemble a ship somewhere in space, then depart for Mars, get into orbit around Mars, take some of that stuff and put it on the surface. That's great. Now remember, the rover that we landed with the 4-to-1 gear ratio doesn't come back, right? We'd like to bring our astronauts back. So we then have to take this, we call it a Mars ascent vehicle, and once the astronauts are done living and working on Mars, which could be as much as 500 days, then they have to take off, and the whole thing has to come back and ultimately land on Earth. So some of the gear ratios that we've been talking about for humans to Mars are perhaps as much as 16-to-1. So that's where the technology comes in. How can we reduce a factor of 16 in order to get 40 tons to the surface to something that's more reasonable, like maybe 4 or 2? It would be nice if you had to take 40 tons to the surface in order to be able to come back, that the gear ratio was 2. We're not quite there yet. Let's see, what else should I say about that? So it's, as I mentioned, it's 8.5 months out, 500 days on the surface, and then 8.5 months back. It's roughly a 3-year journey to Mars if you're an astronaut. So this is our attempt at a bat chart. Unfortunately, we can't ever do the same thing the same way twice because we're the government, and so we've drawn a chart horizontally instead of vertically. But basically, it's going to take science and technology in order to enable the human exploration of Mars. We're going to do it in stages. We have this period of time that we're in right now called Earth reliant. What that means is that as we move out into space, create a toehold in space, we can get home in a matter of hours. Or we're dependent upon Earth to supply us with resources and the things that we need in order to live and operate in space. And today, you can go outside and look in the sky, and if it's just the right time, you can see the International Space Station fly overhead. And there's 6 people living and working in the International Space Station right now, keeping our toehold in space in this Earth-reliant period of exploration. Then, we move to an area called the Proving Ground. We're not exactly sure where that is. It's somewhere between the Earth and the Moon. And the idea there is we could return within a matter of days. If there's a problem, the astronauts could get home in a matter of days. Kind of remember Apollo 13? We had to get those astronauts home fast, right? So we would have a rocket that would get us into that area of space, Orion, which is a crewed capsule that would keep the astronauts alive, coming and going. We would need a habitat of some sort in this proving ground so the astronauts could live and work for much longer than just the amount of time that they did when we were, say, on the space shuttle. And then to move things around, we're working on solar or electric propulsion. It says Asteroid Redirect mission there because one of the things we might do is use this highly efficient propulsion technique to nudge an asteroid into orbit around the moon so that we'd actually have something to work on. So this solar electric propulsion is great if you're cargo. If you're a human, you don't want to use it because it requires a lot of time. It's very efficient, but it takes a long time. So we're looking at other ways of sending humans deeper into space and onto Mars. Then we reach a phase in our BAT diagram called Earth independent. And if for some reason there was an emergency and you had to come home, we're talking matters of months, right? Missions would go as much as 2 years. You can see that like I said, Deputy Chief Technologist can't operate the technology. So we've already got orbiters and landers on Mars. We'll continue to place them there. By the way, for those of you studying planetary science, Mars has 2 moons, Phobos and Deimos, one of which is presumed to be a captured asteroid. We will have some sort of crew module that goes from the deep space habitat to Mars, and right now we're calling it a TransHab, Mars Transit Habitat. The idea is to maybe make it reusable. So it would go and it would cycle out to Mars and come back, and then cycle out to Mars and come back. And we'd have to time it so the astronauts would rendezvous with it in just the right time so they could hitch a ride to Mars. So now I've got a couple of just pictures. NASA's Kennedy Space Center. I've been there many times. If you look me up on the web, you can find my picture in front of this building. It's called the VAB. It's representative, though, of the entire space infrastructure around the United States that's gearing up and getting ready to take us onto Mars. The International Space Station, I've already mentioned that. It is our first home in space, permanent home in space. People come and go, and they live there generally for 6 months at a time. Any of you at Scifest last year? Yeah. I brought with me Katie Coleman. Some of you might remember her. She lived on the International Space Station for 6 months. It was her and 5 guys. That must have been an interesting dynamic. The really interesting thing is, as NASA moves from Earth-reliant to proving ground to Earth-independent, we're leaving a space behind us. Somebody still has to resupply the International Space Station. And so now we've got 2 companies emerging. Perhaps some of you have heard of SpaceX. It was established by a young man from South Africa. His name is Elon Musk. And SpaceX has been already sending supplies to the International Space Station as a commercial entity, kind of like courier. What's a courier name in South Africa? DHL or something like that to the International Space Station. NASA says, we need this food and water to go to the space station, and Elon says, that's great. Show up at this date and put it on top of my rocket, and I'll send it there for you. This is a picture of the Dragon capsule and the cargo module that goes along with it that has docked several times to the International Space Station. In addition, there's another company. So he's not doing this alone. There's some competition. Orbital ATK is also doing the same thing, and they have also sent cargo to the International Space Station. It's not easy. They both have had problems and failures and are trying to recover from them. So it is a difficult thing to set up your own company and get cargo to the International Space Station. But think about whether or not you would want to stay as a DHL courier delivery to the space station. What else does NASA need to come and go from the space station? Human beings. So suppose we set up an Uber space, right? There's a commercial crew program that now SpaceX and Boeing and Sierra Nevada and Blue Origin are all vying for the privilege of carrying astronauts into space. Well, it makes sense, doesn't it, that they would want to get the cargo right first before they actually put humans on top of their rocket to send them onto the International Space Station. But that's what we're doing. We're encouraging commercial enterprise and entrepreneurs to fill the space behind us as NASA moves further and further out. And that's just another picture of commercial crew. We're looking forward to the day when we start launching astronauts to the International Space Station from U.S. soil. We stopped doing that when we terminated the Space Shuttle program. We terminated the Space Shuttle program so that we would have enough funding to be able to build the rocket that will take us to Mars. And when we did that, then the only entity that launches astronauts to the International Space Station is Russia. So we buy seats on the Soyuz module and fly our astronauts today to and from the space station from Baikonur in Russia. And recently, like the beginning of this week, these two fellows returned from the International Space Station. Scott Kelly and Mikhail Karamenko, whose name I can never be sure I'm pronouncing exactly correctly, have returned from spending 1 year in space. Remember I said humans come and go every 6 months, but this was a special medical study to look at what the effects of space would be on the human body after a year. The really interesting thing is that Scott has a twin brother who is also an astronaut, right? And so he stayed, his twin, Mike, I believe, stayed on Earth, and he was the control for the experiment of what a year in space would do to Scott's body. And now they'll both be studied over the rest of their lives to try and understand what this exposure has done to them. I'm sorry? Identical twins, although they don't look identical. Scott doesn't smile as much as Mike. So remember I mentioned that we were going to need a rocket. We stopped building or operating the space shuttle so that we could build the space launch system. And today there's a factory in the United States where you can go and you can see these rocket body parts being made right now. Our maiden voyage of the space launch system is going to be in 2018. On top of that, we need to put a capsule. Remember, the Apollo capsule carried 3 astronauts. This one carries 6. So it's much, much bigger. It's also much, much bigger than the Mars Exploration Rover that you saw. And the idea is it is the safety place, the safe place, where you put this thing on top of a rocket and then launch them into space. They have to be able to return. So this is like the lifeboat back using the Orion module. In addition, I mentioned solar electric propulsion. What you do is you take a gas like xenon and you run it through an electric grid which pulls one electron off. And now I've got a cloud of electrons and I've got xenon ions. And I can accelerate those between 2 grids and then right out the back end of a thruster right here. And that gives me a very efficient thrust. It's very low thrust, though. In fact, I wouldn't recommend it, but if you could put your hand in the exhaust, you would feel only the amount of thrust as much as a sheet of paper creates in weight on your hand in 1G right here on Earth. But if you're patient and you wait and you thrust constantly all the time, you can actually very efficiently send cargo onto Mars. And we've proven that we can do that. There's a JPL mission called Dawn that has visited two bodies in our solar system, Ceres and Vesta, both in the asteroid belt. But without solar electric propulsion, we would have had to send up 2 rockets, 2 spacecraft, and 2 operations teams. In this particular case, we put on a solar electric propulsion system, and it was able to visit Vesta first, and then it orbited Vesta, and then it left Vesta, and it went on to Ceres. In addition, one of the things that we're going to need to be able to do in deep space is know how to do rendezvous and docking. It's very different in deep space when there's less gravity. Up on the International Space Station, it's very predictable orbits, not only for the space station, but also for the thing approaching the space station. But if you're, say, 3/4 of the way to the moon, and you have to rendezvous with a habitat, it becomes a much more difficult control exercise to be able to rendezvous with this thing in space that's really, it's in a very shallow orbit, you know, and it moves. The slightest perturbation, it'll move or twist or flip on you. So we have to develop some new technologies associated with automated rendezvous and docking. And the list goes on. So now I'm into an area of puzzle pieces. What are some of the challenges that will enable us to put our own bat diagram together that will finally be the way we'll get to Mars? You know, we need a space launch system. We need Orion. We need the commercial enterprise to back us up. We're going to need propulsion systems like common chemical propulsion systems or electric propulsion. We'll need a Mars taxi, perhaps to move between Phobos and Deimos and orbiters around Mars. We're going to need chemical propulsion systems. We'll need a Mars ascent vehicle, which is a rocket on Mars. How do you, once you get the astronauts on the surface, how do you get them back? Well, you've got to build your own rocket. The only time we've launched anything off of a solar system body was Apollo. And that was a very nervous time. The 2 astronauts got back inside. We launched a solid rocket. We lit a solid rocket motor that took us into orbit, and there they rendezvoused with a command module and came home. Well, the moon is it's a fraction of the gravity at Mars, and it doesn't have an atmosphere. And so the Mars ascent vehicle is going to, and also needs to carry at least 4 crew. So the Mars ascent vehicle is going to be a huge technological challenge. And I mentioned EDL. How will we get 40 tons to the surface? Now, we probably won't do it all in one shot, but we'd rather not do it in 900 kilogram chunks either. So we're looking at ways to increase our capability to land on the surface of Mars, and hopefully with less terror. We'll need excursion vehicles. Once we get onto the surface of Mars or Phobos or Deimos, we're going to need a way to move around and operate, because you can't just walk on the surface of Mars, right? You need to be able to be in an environment like a submarine almost. There'll be logistics modules resupplying the people living and working in the Mars system. We mentioned the ascent vehicle and the Mars taxi already. There is this habitat that will form the base somewhere between the Earth and the Moon. They call that cislunar space. That will be the departure and arrival point for missions going on to Mars. Let's see. How do you live and work for long periods of time in space? There's lots of issues with that, but the most important, I mentioned TransHab before, but we'll need Mars surface habitats. How would you feel if you had to live in a bus for 3 years, right? With 3 other people. Probably go nuts. So we're doing human compatibility studies, and we're looking also at efficient ways of using robots and automated systems so that we take some of the burden off of the astronauts as we go on to Mars. The challenges associated with our destination systems. How do you land? And What role, if any, does the moon play? We're not sure. Or asteroids. We're still not exactly sure. There's a group of people that say we ought to establish a base on the moon and then go from there to Mars. Unfortunately, that's not what the president has asked us to do. So we're not doing that. In addition, you create a lot of infrastructure at the moon, but your real destination is over here. And so there's a problem of, am I investing too much at this destination in order to get to that one? And finally, we're going to look at robotic systems. How can automated, robotic, artificial intelligence help us go further to Mars and maybe reduce the overall mass or the overall expense associated with Mars? We'll need communication systems. Or this happens to be a picture of TDRS, which is a tracking and data relay satellite system, but it's representative of a satellite that we might put together to communicate with the astronauts as they go to Mars, as they live on Mars, and as they come back. Today we do that with small systems. If the rover's on the surface of Mars, it has a very low data rate up to an orbiter around Mars, and then we send that data home to a dish antenna, kind of like the ones up in Heart of Beastock that we then distribute the data on the Earth. For astronauts, we're going to need a lot more bandwidth. And one of the things that we're looking at is whether or not we can communicate from Mars with a laser. The interesting thing about, and we've done that, by the way, one of my 30-plus missions did that from the moon. We did 680 megabits from the moon with a laser. The interesting thing about Mars is that you send a laser towards the Earth, and it makes a spot on the Earth. Well, when you're communicating with radio waves, the radio waves from Mars, they spread out a lot more. I don't know if any of you got to see the laser show, but Dr. Ashworth did a great job yesterday of explaining the divergence of the light, of normal light, compared to lasers, right? So the light, the radio waves from Mars normally spread out so much that you could fit 3 Earths inside the beam once it gets to Earth, which means it's really kind of easy to find the Earth and lock up so that the two radios can talk to each other. Well, when you use a laser from Mars, the divergence is much, much smaller, and the spot size is only the size of the Eastern Cape. So you can imagine finding the receiver on the Earth with the laser is going to be really hard. And if anything gives you a little jiggle back at Mars, you know, like we've got reaction wheels, the things that keep us stable, or if there's like a tiny little meteorite hit or something, it's going to do this at Mars. But all the way back at Earth, it's going to be doing this, right? And so hanging on to that signal is going to be really hard. So we're working on stabilization systems to assure that we stay that the laser system stays connected. Well, why would we go to so much trouble when we could do it with radio waves? Because we can send so much more data back to the Earth as a result of using lasers. The Asteroid Redirect mission was a concept proposed early on, and we're still working on. We're not sure what the survival of it's going to be, but the idea is to go grab a boulder off of an asteroid and bring it into the space between the Earth and the Moon. Nothing so big as it would harm anybody if it were accidentally to fall to Earth, which it won't. But it's big enough so the astronauts would have a place to visit, right? Like a home base. And also that they could go out and they could practice sampling it, they could practice rendezvousing with it, and that sort of thing. So that's one of the things that we're considering about the Asteroid Redirect mission. If this happens to be a picture of Maven, if you were here just before we started, we were talking about what happened to the atmosphere at Mars. You know, Mars has it's almost the same size as Earth. Earth has a lot of water we've learned, or we're learning, even though it's buried under the surface. But it has this really thin atmosphere. And you heard in the video The one fella say, it has just enough atmosphere that you have to deal with it, but it's not thick enough to actually stop you. So what happened to the atmosphere? Earth has a wonderful atmosphere, right? What happened to the Martian atmosphere? Well, the theory is that Mars, because it doesn't, right now, doesn't have a coherent magnetic field. We have a magnetic field that we can rely on here at Earth. We live like in a magnetic bubble. And that protects us from the solar wind, the particles that the sun emits all the time. And so when the solar wind comes to the Earth, the magnetic field diverts it around the Earth and protects us from being exposed to this solar wind. When it gets to Mars, because there's no magnetic field that's coherent, the solar wind reaches the top of the Martian atmosphere. Those particles come along and they drag some of the atmosphere particles away with it, and they become part of the solar wind. So what the theory is, and what Maven is seeking to prove, is whether or not there has been consistent over the millions of years of Mars' lifetime, just slicing away the top layer of the Martian atmosphere. And is that why it is so tenuous? Tells us a lot about the importance of the magnetic field if that's really true. And we'll continue to land on Mars. Today, it is Opportunity and Curiosity that are roving Mars. But in 2020, we will send another rover to the surface of Mars with more experiments, as well as one that will begin to look at whether or not we could make our own rocket fuel on the surface of Mars instead of having to carry all that rocket fuel for the ascent vehicle and pay the gear ratio tax associated with it. Theoretically, we could launch an empty Mars ascent vehicle, land it on the surface of Mars, and then begin to fill it up so that the astronauts could come home. And in fact, that's what Andy Weir in the book The Martian, the book and the movie Martian, actually proposed that NASA would be doing. So he actually did his research pretty well. So for Jim, what I would say is this diagram needs to be turned sideways so that we can make our own bat diagram. We will leave the Earth. We'll move through cislunar space and our proving ground. And in the 2030s, right now it looks to be about 2035, we will land human beings on the surface of Mars and return them safely after roughly 500 days. And we will continue to explore beyond. This happens to be an artist's concept of an astronaut standing on Phobos, looking at Mars rising over the horizon. I believe that once we get astronauts to the surface of Mars, we'll be looking where to go next. Perhaps it's a space station around Saturn, or maybe it's to Pluto. Maybe we'll have to reinstate it as a planet, though, huh? So I think that that's because human beings have an innate desire to explore, to see what's next, what's over the next rise, what's upriver, what's across the ocean, what's across the sky, and on to the next planet. So that's where you can go to find out more about NASA and its journey to Mars. I appreciate the fact that you listened. I hope I didn't talk too long and you didn't fall asleep very much. But do we have time for questions? So thank you very much, and we can do questions.
Questions? Woo! We're going to be here for a while.
Oh, are we? Awesome. So one of the ways I work is if you ask a question, you get a NASA sticker.
Okay, so
but I want questions from the younger audiences as well.
All right. Okay, so I'm going to say hands down and then shoot up again. No, I'm kidding. Okay, I think there were about like 4 questions, so let's start in the corner and then work our way down. I think it's just going to be the best for the mic. Dave.
Jim, the Apollo crews were selected quite some time before the orbiting and moon landing, so they were training for many years. Have you already selected the Mars crews?
Well, we've selected the next round of, or we've actually put out an application. Maybe we could You could also ask the usher to pass out the stickers or Stephanie. We are constantly refilling the ranks of the astronauts. The astronauts, they come and they work with us for 10, 20 years. In the case of Katie Coleman, she's a 20-year veteran. But then eventually they retire. And so we need new astronauts. Maybe some of you will be an astronaut. Normally we get 500 applicants for a class of 15 to 20, right? This last round closed last month of applicants, and we got 18,000 applications. Wow. There are a lot of people that want to be part of the journey to Mars. It's a great question. Who's next?
Hi. I was wanting to ask about the beginning of your lecture with the video. There was a lot of stuff that fell off.
Yeah.
What happens to all of that stuff? Do you guys ever reuse it? And also, you guys have got 2 rovers on Mars. Do they ever run into each other?
Okay, great. That's a great question. Stephanie, can I just ask you to take those are 2 great questions. One is Mars is a big place. It's about 2/3 the size of the Earth. We intentionally landed them in different places. Why would we do that? Because it's a big place and we want to know about it. You know, it's a very diverse environment. Even though it may not look like it in the still pictures, it's a diverse place. So no, the rovers never run into each other. In fact, the rovers don't move very fast at all. Even the big one doesn't move very fast. About 100 meters a day. So you can imagine if you ever wanted them to go meet each other, it would take an extremely long time. Second question was, first question was, what is all that stuff, right, that you're throwing off? So no, we don't go around and pick it up. It all lands on the surface of Mars. At some point, it's throwaway.
Naughty NASA.
Naughty NASA. We're littering NASA. In fact, if you Google, there's a really cute video. It doesn't have anything to do with NASA, but if you Google the video Martian Spring, it's really quite funny about all of the debris on Mars, right? But you know, that's the stuff that we need in order to get to Mars. We need to release a heat shield. We need to deploy a parachute, and then we don't need it anymore. And then a back shell, right? And then ultimately the sky crane. All of that stuff is necessary in order to put the 900-kilogram rover on the surface of Mars.
So there's also potential for a scrapyard shop on Mars
Yeah.
one day.
Well, in fact, if you watch the movie The Martian, that plays a role in all of in Mark Watney's survival. That's an awesome question. One more factoid about that. You may or may not have noticed, but as the rover began to start its entry, this is before the heat shield heats up and before the back shell is off, you saw bits of like debris coming off the perimeter of that circular back shell. That was actually, I was surprised that they actually put it into the animation, but that's actually to change the center of mass of the system so that it would give us just a little bit of lift as we came through. Remember, one of the EDL engineers said we're actually flying it through the atmosphere? That was so that it would fly through the atmosphere like a wing. But the interesting thing is that in order to deploy the parachute, we had to go flat again. So then we threw off the same amount of mass to move the center of gravity back, right? Not a very efficient way of doing it. Well, I mean, it's a very efficient way of doing it if you're an EDL designer, but not a very efficient way from mass, because each time we threw stuff off, we were losing 40 kilograms. And it was just 40 kilograms of dead weight. So somebody came up with this idea of, well, let's ask the public, what would you do with those 40 kilograms? And so we held a competition to find out what some of the best ideas are out there to utilize the 40 kilograms for the next landing. So I think that some of the really great ideas center around creating probes that would also continue on through the entry, descent, and landing phase that then you could watch from orbit and see how they responded to the atmosphere. It's an awesome question.
Okay, I think Nikki, were you next?
Sorry. I heard that NASA was considering, when we send astronauts to Mars, they were considering sending a team of women because women can basically do more work with less food.
Oh.
Is that a thing?
We can do much more with much less all the time anyway.
I just mean that our bodies are more productive, like higher productivity.
Yeah, that's the first time I've ever gotten that question.
You take that back to NASA.
So, to my knowledge, the gender of the astronaut and the stereotypical perception of a particular gender's ability to perform has not been a factor. What is a factor is the testing that each individual astronaut has to go through. And we look at the uniqueness of each astronaut. Perhaps you're too tall for this particular mission, right? Or maybe you're going to be using certain kinds of controls and your arms have to be a certain length. So we do measure that kind of stuff. But I've not ever heard.
And he doesn't blush often. All right.
That's a great question. So make sure to give her a sticker. Right?
Thanks. I'm going to keep it to Nikki and then I'm going to move down in this direction if that's okay. Yeah.
I want to know if you are considering self-sustainability in any of the phases and kind of working with environmentalists on the possibility of what can grow and that kind of thing.
Yes. In fact, I was up in Boston at the MIT Media Lab just last month where we were looking at what a greenhouse might look like on Mars. Absolutely. The problem is, to begin with, there aren't the nutrients in the soils at Mars like there are here on Earth. So you can't just take seeds along with you and put them in the Martian soil and expect them to grow. You'd have to take some of our own growing systems, some of which may not involve soil at all. Hydroponics might be one of those things. So we're looking at that and trying to see how might we especially get green food to astronauts on their way to Mars and on the surface.
Okay.
It's a good question.
Nick?
Thanks.
Jim, are you not seeding Mars with life with all the bacteria that's hitching a ride on all these missions?
So there's an international community sponsored by the United Nations called COSPAR. COSPAR sets standards for what kinds or how clean you have to keep a planet as you're exploring it. The moon, not so much. You know, we left a lot of waste on the moon, including human waste. Right? It's a lot like exploring Antarctica, right? You don't want to damage the environment that you're trying to understand. We know for a fact that when we send humans, we're going to contaminate. It's just a fact of life. We take that as a challenge, though, to minimize our footprint. When we send these rovers, though, to Mars, the lander, like the Viking lander, we baked it for a week in an oven to assure that we reduced as many of the microbes that were on it as a result of being assembled by human beings as possible before we shipped it off to Mars. When the Curiosity rover was built, we wrapped its wheels in plastic bags to assure that we weren't taking any earth along with it. And there were standards about clean rooms and how closely monitored were the surfaces of those rovers. So we're trying to meet the policies that COSPAR sets for exploration of planets beyond. The other interesting thing about that is we want, the COSPAR says, is we are also concerned about bringing stuff back. So you can imagine, what would you do? We don't have an answer to this question yet. What would you do if you have a successful mission to Mars with astronauts? They go to Mars, they land, they spend 500 days there, everything's going great, they get in the ascent vehicle, they come back, and on the way back, remember it's 8.5 months, one of them gets sick. You do. Right? Kick him overboard?
Write a book.
or you know, hopefully we'll be able to diagnose it as something that we know from Earth. Right? But if you can't, then we've got a problem. We've got to figure that out. Are we bringing toxins back to the Earth? And that's what we call planetary protection. And there's a community around the world that gets together to try and discuss these issues to assure that we're not going to, one, damage the science that we could do at these destinations. And it includes the moon and asteroids and all of the planets. And two, assure that if we were to bring samples back, we've got the right kind of containment and quarantine to assure that we aren't putting human beings here on Earth in harm's way. That's a great question.
There's another sci-fi movie in that. Okay.
Yeah.
Are there any questions from the learners in the front before I move in that direction?
Yeah.
Two here.
Oh, there we go.
Jim.
So can we
Right.
give them a
Microphone. Here. Chris, you're here like the whole afternoon.
I just want to ask, to drive a rover, does it drive itself or do people in Earth drive it?
That's a great question. So, have you seen radio-controlled cars? It doesn't work like that at all. It actually works a little bit. But there are such things as rover drivers. And if you were at Scifest last year, we had a Skype session where the audience was able to interview live 3 of the rover drivers from the Jet Propulsion Lab. So there are drivers, but think about the problem of driving a rover. A rover is on Mars, and the time for the radio signals to get from Earth to Mars varies from 7 minutes to 21 minutes. So you could say turn right, but the rover won't know that you said turn right for as much as 21 minutes. So how do you deal with that? What do? That's where autonomy, artificial intelligence, and automated systems come to play to assure that the rover stays safe and can actually execute the commands that you want. We also need better, much better resolution imagery of the environment that the rover is moving through. That's an awesome question.
Okay, so I'm going to take the lady in the blazer, gentleman in the green, lady with a striped jersey, and then I'm going to call it quits for the afternoon. Because you need to get to Rhodes, sir.
Oh, that's right, I got to do this again.
So, what kind of technology would we need to minimize the carbon dioxide in Mars?
To minimize the what?
The carbon dioxide in Mars.
Carbon dioxide. So we don't need to minimize the carbon dioxide is naturally occurring at Mars in the atmosphere. It's like 80% carbon dioxide. So we wouldn't minimize our contribution of carbon dioxide, but there are technologies that we're looking at that would take carbon dioxide and break it down into oxygen and carbon, so that then we can use it. Have you guys done an electrolysis experiment in natural sciences yet? You take water and a battery, and you have these 2 electrodes, and put a little salt or acid in there. You get bubbles off the electrodes, and you get what? Hydrogen and oxygen, right? Right? You can capture that. Well, that's one of the things that we're looking at, is whether or not we can make hydrogen and oxygen from the ice that you find at Mars. Same way, we're looking at whether or not we can crack open the carbon dioxide and make oxygen and carbon. Once you have hydrogen, carbon, and oxygen, then you can begin to make some real materials at Mars, perhaps methane, so that we can use that as a rocket. You can also use hydrogen and oxygen. It's a great question.
Okay, next.
Hi, thank you. I just have 2 questions.
That's cheating.
It's 2 quick ones. First, what is the current cost when you're considering like everything that is happening currently with the rovers that are there and how you got them there, and what is the estimated cost afterwards, like when you eventually get the humans across to that side?
So,
and also, sorry, the second one, with regards to like everything, like all the problems that are currently being faced by the planet, like ecological problems and social problems and so forth, how do you justify spending so much money on, you know, extra planetary things as opposed to, you know, everything else?
Yeah, those are good questions. So, number one, a rover like you saw in the video landing is about $2.5 billion. It's not cheap. When you do the design, development, fabrication of it, testing of it, the cost of the rocket, the operations team to get to Mars, to land it on Mars, and then to operate it for 2 years at least on Mars, it's an expensive prospect. And so it's fair to ask the second question that you asked. The question of what is it going to cost us to get to Mars, we've been trying to estimate that cost since 1960. And every time we do, we get a huge number, and we say, oh, we can't afford it, we need to go back to the drawing board. So the next round of cost estimating for the journey to Mars is going to come with some sort of cap, some sort of wedge, and say, okay, here's the operational cost that we're willing to spend. We haven't set that number yet, so we don't know exactly. But you can guess that it's going to be more than $2.5 billion. Right? So that's the answer to your first question. The second question is, I find it a privilege to work for NASA. NASA is an agency of the federal government, and the United States government has decided that they want to have a space program. And as long as the public elects leaders that says this is valuable to the United States, then I'm going to work for NASA, right? So I don't emotionally have to justify it. I do know that there are other things going on in the world that are heartbreaking, right? However, when you start looking at the space program worldwide, the NASA budget feeds a $330 billion a year industry that keeps people alive in space, that keeps data flowing, that enables us to have cell phones that work, right? And then creates a stream of technologies that entrepreneurs can keep utilizing. So NASA's, of that $330 billion a year, NASA's budget is tiny, tiny, tiny compared. But what we do is we make all of our technology available to entrepreneurs. And things like baby formula come out of it, or better padding in bicycle helmets, you know, or better ways of identifying whale sharks. You know, if you had come to the lecture I gave last week, there's a whole collection of what we call spin-offs that come from entrepreneurs that take NASA technology that was designed to go to space and utilize it right here on Earth. So in that way, I feel NASA is making life better right here on Earth. In addition, we inspire learners like these to study math and science, to do well in school, to set a vision to move forward and to hopefully change the Earth and make it a better place. I love that question. Thank you.
And I think not forgetting, of course, all your satellites and what they do for food security and water security on the planet.
Absolutely, yes. We've got weather satellites that will tell us how the weather's going, and climate change satellites that will tell us longer term whether or not we're expecting droughts and how is that happening, what's happening to the Earth. We've got security satellites. Every nation needs security. We've got security satellites. So a lot of that is technology that then makes the world a safer place.
Yeah. Last question, please.
I think it's me, sorry.
Where are we?
On the right, far right.
I just wanted to ask, because I know that there's been competition between all countries in the world since space exploration began. So does NASA have like a monopoly over Mars, or like how does it work? Like have you, is there like a co-management situation with different scientists from all over the world, or yeah?
Yeah. So that's a really good question, because if you recall, we coined this phrase called the space race, right? And that was in order to try and get U.S. astronauts to the surface of the moon before the USSR, the Soviet Union's space program did the same thing. Today, we don't do a mission without international collaboration and partnership. In fact, the European Space Agency is made up of many nations that have come together to try and create a unified space agenda. NASA is not part of the European Space Agency, but we do collaborate with ESA a lot. The International Space Station, 12 different nations have come together to create a place where we can study space together. So, from my perspective, we don't have a space race anymore. That was 1960s. Today, what we have is a spirit of collaboration to help humanity benefit from the exploration of space. And it's harder, believe it or not, to sell a program of peace rather than a program of competition. But that's where we're going, because it's not the right thing to do, to say the United States got to Mars first and we plant our flag and now we own it, right? We're not going to do that. We're going for all mankind.
Then perhaps you should change your slide to say launch the world as opposed to launch America, yeah?
Yeah, maybe I should.
We'll chat about
well,
that
actually,
later.
that's a bit of nationalism as well. Yeah.
I was expecting NASA music to come blaring over the speakers at any moment. Jim, I'm going to end the session there. Thank you very, very much again for the week that you've spent with us, the time that you've invested in Scifest Africa. I know you are speaking on the Roads program now, so we need to get you to the university. But we've already given you all the other bling. But this is to say thank you very much.
Oh, thank you so much. Okay.
Thank you very much, ladies and gentlemen.